Hello and welcome to chapter 4. We're working our way through the OpenStax OER Chemistry 2 ebook, and this has been a really great time. In this one, we're going to be writing and balancing chemical equations, super important. We're going to be classifying chemical reactions, also very important. We're going to be doing reaction stoichiometry. Okay, and stoichiometry is often considered very difficult for students. So we're going to be taking it as slowly as we can and really working through it. And whether you're meeting with me in class or you're taking this online with me and have Zoom sessions, you know that there will be times when you can ask for help. So don't worry too much about that if you've heard horror stories of stoichiometry. Reaction yields, which is really a part of stoichiometry, and quantitative chemical analysis, which is a little bit about the math and things like that that are going on when we're in the lab. All right. Okay, so let's take a look here. Now we have chemical reactions and balanced equations. Now, chemical reactions and balanced equations, the big thing with this is that what we're doing is we're working out of that law of conservation of mass. And remember, the law of conservation of mass says that what cannot be, that matter cannot be created or destroyed. Okay, it can, but it can change, it just can rearrange itself, right? I'm getting it mixed up with our thermochemistry, which is next chapter. Okay. So matter can be created, matter cannot be created and it cannot be destroyed, okay? But it can change the way it's organized. So on this side of our equation, we have one carbon here, and we have 4 hydrogens here, and here, and here, and here. Okay, and then we have 1, 2, 3, 4 oxygen atoms. And now when we come over here, we can see that we have 1 carbon here in the center. And we have 1, 2, 3, 4 hydrogens over here. And now if we look at these here, we can see that we have 1, 2, 3, 4, and we have 4 oxygen atoms. Okay, and this is what that law of conservation of mass is telling us. Okay, if we have these atoms on the reactant side, that's the left of the arrow, then we have to have the same ones on the product side. Now, when we're looking at it as a balanced chemical equation, we can read this as 1 mole of methane reacts with 2 moles of oxygen gas. Remember, oxygen gas is diatomic. So in these reactions, if it is oxygen gas, we have O2. If it's hydrogen gas, we have H2. If it's nitrogen gas, we have N2. Grab my periodic table. I always have to look at a periodic table. Remember where we have our diatomics. Okay, fluorine, chlorine, bromine. Okay, the only gases that are single elements, oh dear. I just made a mess. Okay. Never mind. Don't worry about it. Okay. So the only ones that are not diatomics are noble gases, and they're not going to be reacting for the most part, so we don't need to worry about it. Okay. So 1 mole of methane, 2 moles of oxygen, okay, form 1 mole of carbon dioxide here and 2 moles of water. Okay, now let's take a look at how some of these work. So here's a reaction between methane and oxygen gas. And what I'm doing here is I'm showing how many of each thing we have. And you can use a process like this for balancing things as well. All right, so let's take a look now and let's do this kind of a balancing method again. Okay, so here we have H2O and H2 and H2. So water forms hydrogen gas and oxygen gas, and we need to make sure that we're balanced. So kind of the foolproof way of doing this, and you might get to the point where you don't always need to do this, but that's to say, okay, well, here I have hydrogens and I have oxygens. And on my reactant here, the H2O, so one, right now I have 2 of the hydrogens and 1 oxygen. And now on my product sides, I also have hydrogen and oxygen. Okay, and I have 2 and 2. Now, notice that you can't just add another oxygen to your left side. You can't just add another oxygen to your reactants. You have to add another complete water like this. Okay, well, now what we have is we have 4 hydrogens and 2 oxygens. So I can come over here and say, okay, well, my oxygens are balanced, but my hydrogen isn't. I'm going to add another one of those. And now I have 4 hydrogens, 2, 4, and 2 oxygens. Now I look at this and I say, okay, I am balanced. So I can write these in. And so I see that I have 2 waters, 2 hydrogens, and I have 1 oxygen gas. You can leave this one empty if you want to. However, when you're taking your quizzes in Brightspace, or if you're taking a fully online class and you're taking tests in Brightspace, if you don't put a 1 in, it's going to auto grade it as incorrect. Okay. And I always say in the classroom, put a 1 here, because then I know that you didn't skip it. I know that you actually knew it was oxygen. Okay. Now let's come over here and we'll look at our next one. Now this next equation has nitrogen and oxygen in it. And on the reactant side, we have 2 of each atom. And on our product side, we have 2 of our nitrogens and we have 5 of our oxygens. Okay, well, that won't do. Now in this case, what I'm going to do is I'm going to say, okay, my nitrogens are already balanced. And I have 1 over here. So let me see if I can just sort of kind of see where that is. And this is what I mean by this. I say, okay, well, if I have 2 oxygens and 5 oxygens, I know that this needs to come to 10 each. Okay, so let me just sort of think, because I have a pen that erases. So always good to do things with pencil. Now, but let's take a look at what happens here. So if I have 10 oxygen units here, then this would be a 5. And if I have 2 of my N2O5 units, this would be a 2. Now I can see that 5 times my O2, I have 10. And 2 times my N2O5 means I have 10 oxygens. Okay. And now on the product side, 2 times the N2, I know now that I have 4. And I think, oh, well, could it be that easy? If I know that this needs to be 4, then I must have 2 nitrogens. All right, now let's take a look at one that is a little bit longer. And we have C2H6 plus O2 yields H2O and CO2. So now we don't have just 2 elements, we have 3 to worry about. C, H, and O, carbon, hydrogen, and oxygen. Right. Now, once it starts getting to be a lot, especially with this one, where in our product we have oxygen in both places, it is really good to keep really careful notes here. Okay, now in our reactants, we have 2 carbons and 6 hydrogens and 2 oxygens. And on our products, we have 1 carbon, we have 2 hydrogens, and we have 3 oxygens. And we think to ourselves, well, that is just a mass. Okay, so the first thing that I would do is, okay, so here's a trick. Leave the oxygen to last because it's everywhere. And so we don't want to confuse ourselves by trying to do the oxygens first. The thing that I would look at first here is I would say, oh, see this high H2 and this H6? All right, let's do this. Okay. Now I have 3 waters, okay? And that means that I have 6 hydrogens and I have 1, 2, 3, 4, 5. Oh, I have 5 oxygens, goodness. Okay, and now I have, no, I haven't changed that yet. Let me see if I can get rid of that little line. Oh, there, okay. Oh, I wrote that wrong. My apologies. All right, there we go. Okay, that was still a 6. Okay, so and now I look here, I say C1, I have 1 carbon. Okay, so let's go ahead, let's take a look here. And I'll say, okay, well, so I need to add another CO2 unit over here. And so now I have 2 carbons kind of go like that. Okay, and I have 1, 2, 3, 4, 5, 6, 7. 7 oxygens. Okay, 2, 6, 7. Ugh. How do I make 2 into 7? Okay, well, let me start here. So right now I have 2 of those, and I have 3 of those, and I have 1 of those C2H6s. And how do I do this? Well, O2, I want 7 of them. So this isn't molecules, this is moles. Okay, well, so I can say I have 3.5 O2 units. A lot of times it's easier to start here. Okay, this isn't my final answer, 1, 3.5, 3, and 2. So now what I want to do is I want to come up with a final answer. And so what I'm going to do is I'm going to multiply each one of these by 2. So this will become 2 times 1, 2 times 3.5, 2 times 6, and 2 times 2. Okay, and I wrote that out so that I could erase all these. Like that. And so this would become 2, 7. Oh, I shouldn't have written 2. I had 3 there. 2 times 3. Sorry. 2 times 3 is 6. And 2 times 2 is 4. All right. Now, whenever you do this level, it's always good to check at the end again. So 2 times C2 means I have 4 carbons. 2 times H6 means I have 12 hydrogens. And 7 times O2 means I have 14 oxygens. Okay, and then on this side, I have 6 H2, so I have 12 hydrogens. I have 4 carbons, good. And now I have 6 H2O, so that's 6 oxygens, and 4 O2, that's 8. So 6 oxygens from my water and 8 oxygens from my carbon dioxide. 6 and 8 is 14 oxygens. Okay, so then I say, okay, I always will do this again at the end to check when I have a very challenging one like this to make sure that I didn't add something incorrectly. All right, now let's come back to one that's a little simpler again. Here we just have nitrogen and hydrogen again on both sides of our equation. Okay, and on my reactants, I have 2 of each. And on my products, I have 1 nitrogen and 3 hydrogens. So now what I'm going to do is I'm going to say, okay, well, let's make this. Let's add another ammonia. And that'll make our nitrogens match. And it'll make our hydrogens 6. And then I come here and I say, oh, well, if I now need 6 hydrogens, I'll just add 2 more of these. Now I have 6. And this one was a simple one again, because it's 1 nitrogen plus 3 hydrogens yield 2 NH3. And that's how you balance fairly simple reactions. We'll be balancing more as time goes on in these slides. All right. So let's take a look. Now, in many reactions, so in our previous examples, we did not have any states. And a state is gas, liquid, solid, or aqueous. Okay. Now, when it is required for you to show states. Okay. So most of the time, unless if I give you an equation with no states in it, don't worry. But if I give you an equation with states in it, you must carry the states through and they must be correct. And the reason for that is that in many cases, especially once we get into thermochemistry, the states will determine part of the stoichiometry. It's very, very important. And here you can see we have 2 moles of solid sodium plus 2 moles of liquid water form 2 moles of aqueous sodium hydroxide and 1 mole of hydrogen gas. And this aqueous, we'll get to this. We've already actually done this a bit. So this aqueous, just remember, means dissolved in water. And you are going to need your, to remember the things that we did from chapter 3, that molarity and things like that are going to be very, very important. Okay, now another thing you'll notice down here in this one, oh, that should be CO3. I must have lost the formatting, solid. yields, and you got this little delta over it, CaO plus CO2. Actually, I'm going to make a quick note. See, this is how I catch my mistakes. Okay, now this delta over the Greek letter delta, in this case, it means heat. It means that this reaction only exists if we have heat with it. You might also see something like this one up here. See the 2 sodium plus 2 H2O. You could also write something like this. Oh, hang on. All right. You could also write something like this. 2 Na solid plus in the presence of water yields. Oh, no, actually, you couldn't do that for this one. I'll show you that one later. That's for dissolution. Okay, don't worry about that. Okay, so let's take a look at some different types of chemical reactions. The first one is what's called a precipitation reaction. And this happens when dissolved substances react to form one or more solid products. And you can also see them called double displacement, double replacement, or metathesis reactions. And they just have some different names. Many reactions of this type involve the exchange of ions between ionic compounds in aqueous solution. And here they're saying many reactions. All of the reactions, all of our precipitation reactions will involve the exchange of ions between ionic compounds in aqueous solution here. Okay, precipitation reactions are common in nature and in industry, and they happen all the time. So basically, well, let me show you on the next slide what that's going to look like. Okay, so precipitation reactions occur when 2 soluble ionic compounds dissolved in water form an insoluble precipitate. Okay, well, what does that mean? Well, that means that here you can say that 1 mole of CaCl2 in its aqueous form plus 2 moles of AgNO3 aqueous yields CaNO3 aqueous and silver solid. So what you can see happened here is that your calcium and your nitrate, those stayed in solution, see? Those are still in solution. And then you've got your chlorides and your silvers. Oh, but those got together to form a solid. And this solid is our precipitate. And when you start working on some of your chemical reactions lab, either in class or watching the reactions on the computer, you will be able to see a lot of precipitation reactions, and they're pretty fun. Okay, so when ionic compounds dissolve in water, so now we kind of see our dissociation reactions here, where we see our calcium chloride forming calcium ions and chloride ions. And then we have our silver nitrate forming silver ions and nitrate ions. Okay. You could also do a dissociation reaction for this last one. Calcium nitrate is actually calcium ions and nitrate ions. Now these ions, let me erase my single compounds like this. Now everything that I have underlined here are all like that in water. So CaCl2 aqueous looks like this. Okay. And AgNO3 looks like this in solution. And calcium nitrate looks like this. So there's no calcium chloride bits in solution. They're all apart in the calcium ions and chloride ions. And it says here, silver chloride is not soluble in water, so it remains in its solid form. Okay. So let's take let me draw a little picture here. Let's say that we have our beaker. Okay, and it has water in it. Okay, and in the water, what this would look like is here at the bottom, we would have our silver chloride. Well, it might be at the bottom, and it might also be suspended through, but that's okay. here at the bottom, we have our silver chloride, and it's fallen out of solution. And then in the rest of the water, we have the things that are left over here. See, we have this calcium nitrate. So after the reaction, we have our silver chloride at the bottom, and then we have our calcium ions, and we have our nitrate ions. And that's the ratio that they're in. And this is what our finished product looks like. All right, so ionic compounds dissolved in water are more realistically represented as dissociated ions. But then it's kind of bulky. So before, on the previous one, we had our molecular equation where everything looked like it was a molecule, even though it wasn't. And what that means is they're stuck together in kind of what their associated ions would be if they were stuck together. However, sometimes more commonly, we will use what is called a complete ionic reaction. And that equation that we had before, we had our calcium, okay, and our nitrate. And our calcium and our nitrate stay in solution. They're called spectator ions. Okay, but here you can see that you have these chloride ions and the silver ions. Those change their form. And if we put just those together, we have what's called a net ionic reaction, which is a reaction that the net ionic equation shows only the reaction that's happening. We'll use the word occurring. I don't know why, because I can't spell it. Okay. Oop. Okay, now let's take a look at a little bit more at these reactions. We have solubility. Now, solubility is really, really important. Okay, so there's a little break in the screen. That's because I had forgotten to pull up another document that I wanted behind this. Okay, sorry about that. Solubility, the maximum concentration of a substance that can be achieved under specific conditions. Okay, so remember, we're making concentration here. The solubility, we are, can be described as a molarity, remember from the previous chapter. Substances that have a relatively large solubility are said to be soluble. Okay, and a lot of times, one way to look at this is say, okay, well, is it more than 90% soluble? Okay, that in those cases, then most of the time you're not going to end up with a precipitate. Okay, a substance will precipitate when solution conditions are such that its concentration exceeds its solubility. Okay, now substances that have a relatively low solubility are said to be insoluble. Now, a lot of times places will also say marginally or slightly soluble. Now, the trick with marginally and slightly soluble is that, yes, some of it goes into solution, but most of it will precipitate out. So if you're asked, is it soluble or insoluble? You should say that the marginally and slightly soluble things are insoluble, because what we're really looking for is whether or not they're going to go into solution, and very little of it actually will. Okay, so let's look at some options for that level of solubility. Okay, and you do have a solubility handout. Okay, let me, I realize I can't easily toggle to it. So I'll show it at the end. Okay, so here we have soluble compounds contain. Okay, and it's group 1 metal cations and the ammonium ion, the halides, the halides from the halogens, the acetate, bicarbonate, nitrate, chlorate ions, and sulfate ions. Okay, that means soluble compounds will have your ammonium, NH4 plus, your group 1 metal cations. Okay, group 1, remember, are your alkali metals. So lithium, I need a periodic table so I don't forget any, lithium and sodium and potassium and rubidium and cesium, but we don't usually go that far. Okay, now you'll notice here it says, okay, so this is that first one here. You notice with that first one, terrible line, that we have no exceptions. No exceptions. That means that they are always soluble. Another always soluble here are nitrates, NO3 minus, okay? And this acetate, bicarbonate, and chlorates don't really have exceptions either. So acetates are C2H3O2 minus, okay? Bicarbonate is HCO3 minus, and chlorate, ClO3 minus, okay? These are a bunch of things that are pretty much always soluble. Now we notice here that the next thing is it says the halide ions. Now that's fluoride, chloride, bromide, iodide, okay, commonly. And they tend to be soluble except here, okay? So that means silver chloride or mercury 1. So this is silver ions. This is Hg22 plus is mercury 1. So you could say mercury 1 bromide maybe. Okay, that would be insoluble. Another one, lead 2, tends to be insoluble. We'll put that with the iodide, PbI2. Okay, so when you put your halides, your halogens with silver, mercury, or lead, then they're going to be insoluble. But not if you put them with, say, nitrate. That's gonna remain soluble. And you'll see in your bright space that there is a very good handout that's very comprehensive. Okay, so now insoluble compounds tend to contain carbonate, chromate, phosphate, and sulfide, and hydroxide. Okay, so these things that tend to be insoluble are anything with a chromate, carbonate, chromate, CrO4. Make sure that I use the right one. There's some that are soluble. Okay, and sulfides, S2 minus. Oh, sorry, the CO3 was a 2 minus. Phosphates, PO4, 3 minus, and hydroxides. Okay, so anything made with these ions is usually insoluble. Okay, and here they say, now some soluble exceptions are compounds of these anions with group 1 metal cations or ammonium, okay, for the top one, and for group 1 metal cations and barium. Okay, so your exceptions over here is that it would be soluble if you had NaOH or KOH, or if you had potassium chromate, CO3. Okay, so again, the handout has more detail, but this is kind of how you use these rules. And so we'll be looking at them and we'll be taking them apart. If you don't know this really, really, really well, you should spend a little bit of time with it. Go back to chapter 2, even if you aren't able to make these correctly without too much stress. You're also going to need these two things with you for pretty much everything in this chapter. Okay, so now let's take a look here. Consider the reaction between aqueous potassium iodide and aqueous lead 2 nitrate. Okay, so what they want for this is they want us to balance and determine the states for a molecular equation, a complete ionic equation, and a net ionic equation. Okay, so first of all, it says balance and determine the states. Okay, well, potassium iodide, we know because of that potassium and the iodide that that's going to, whoops, silly me, that is going to be aqueous, and they tell us up there. And we have this lead nitrate, lead 2 nitrate. Don't confuse that with lead 4 because lead 4 tends to be soluble more often than lead 2 does. So lead 2 nitrate, but it's with a nitrate, so this is going to be aqueous. Now we have our lead 2 iodide. And if you go back to the previous slide, you would see that that is where we have an insoluble exception to the halides. And so this would be S for solid. Okay, and then we have KNO3, and we know that potassium and nitrate, those are always going to be aqueous. Okay, so now let's go ahead and let's balance it. Now here is a fun trick. If you try to take apart these polyatomic ions, it's going to make balancing it really, really difficult. So look at this nitrate here and this nitrate here. Keep them together when you're balancing it, and you'll actually find that this works really easily. See how in our reactants we have 2 nitrates and here we have 1. Usually you can just put a 2 here. Okay, and now here we have PbI2, and we see that we have 2 iodides. So I'm just going to put a 2 right here. And now I have 2 potassium iodides. Okay, and I look through here and I say 2, okay, well, that would be a 1, and that would be, oh, I forgot a line. So that would be a 1 as well. And you can usually just back and forth that to come up with where it should be. Okay, so that's my overall reaction. Now let's come up with a complete ionic equation. So I have my potassium iodide and I have 2 of them. So I'll start with that becomes 2 K plus aqueous plus 2 iodide aqueous plus 1 Pb. Now see how it's PbNO3 2. That's how I know that it's lead 2 plus aqueous. And but there's 2 here. So that means I have 2 nitrate ions, and those are aqueous as well. Okay. Now, if this slide is very challenging for you, and I have a couple of them, I know that I have a couple of additional videos for how to do these, and they will be linked in your Brightspace account as well, just to really break those down with the steps that you're using. It's a little differently than how I'm doing it here. So if this doesn't click for you, there are those resources. Okay. Now I come up here and I have PbI2 solid. So that's going to stay as it is. 1 lead 2 iodide, PbI2 solid. And that stays together because whenever something is solid, it just stays. And then we have 2 potassium ions, and those are still aqueous, and 2 nitrate ions, and those are still aqueous. Okay. And now I need a net ionic equation. And in a net ionic equation, what I'm doing is I'm only keeping the things that are reacting. And I have 1 lead 2 that's aqueous and 2 iodides that are aqueous. And they're forming 1 single PbI2. All right, great. So that means my net ionic equation, see how my potassium and my nitrate are the same on both sides? They're spectating. They're not actually participating, so we don't really care about them. Okay, so, and I like to write with my cation first. So I have 1 Pb 2 plus aqueous plus 2 iodide ions aqueous yields 1 PbI2, 1 lead iodide solid. And that is the end of my net ionic equation. Okay, let's take a look at another one. Okay, here's another one. Aqueous sodium chloride and aqueous silver nitrate. All right, so let's take a look now. So here it said that we have aqueous silver chloride and aqueous silver nitrate. And then I go back and I look at my solubility rules and I see, oh man, that silver paired with halides is a solid. Okay, it is insoluble. But sodium nitrate, anything with sodium and anything that's nitrate in them, those are definitely going to be aqueous. Okay, that's why they're so useful, because nitrate is one of the few things that you can put on silver or lead 2 or mercury 1 and make it soluble. So if you want to do a reaction and you want those silver ions available, then you can start by using a silver nitrate solution and you put it in water, the ions come apart and it will stick to whatever anion that you put in with it. Okay, so now let's go ahead and look at these again to balance it. And actually, this looks really simple. See, oh, look, everything is one nitrate, one silver, one chloride, one chloride, one sodium. So everything in here is 1, 1, 1, and 1. It's all 1 to 1. And that's because everything in here is either a +1 or a -1. Okay, so now let's take a look again at our complete ionic equation. And we have, I'm going to leave off the ones because they're all 1. So we have Na plus aqueous plus Cl minus aqueous plus silver ions, Ag plus aqueous plus NO3 minus aqueous. And when that comes together in my beaker, my lead, my silver and my chloride hook up together. Hang on, making mistakes. My silver and my chloride hook up together to make a solid precipitate. And I'm still left with some sodium ions and some nitrate ions in solution. Okay, and then my net ionic equation only looks at the part of the solution that is reacting, and that would be my silver ions. Ooh, that should be an AQ, plus my chloride ions, also aqueous at this point. When they come into contact, they form my silver chloride as a solid. Okay, so those are precipitation reactions. Let's switch gears a little bit and we'll look at our acid-base reactions. I'm going to be finishing acid-base type reactions and then taking a break and finishing chapter 4. It's kind of a long chapter in the next video. So not super long. I didn't realize chapter 3 was getting crazy long. Okay, so here we have an acid-base reaction is one in which a hydrogen ion, H+, is transferred from one chemical species to another. So what could we mean by that? Well, you could say HCl aqueous plus H2O aqueous forms chloride ions and H3O plus. In this case, we've transferred that. All of the strong acids will do this type of a reaction. Okay, and then we have some weaker acids that don't do it quite to that level. So an acid is anything that will, see here they say transfer, but the language that I've seen that I like better is that an acid is a proton donor. Okay, that means it contains H plus that will become, well, we'll say that will dissociate. And that's what makes something an acid. And something that's a strong acid means that it comes apart completely. So if it's a strong acid, then you're getting a 100% dissociation. So you could say also H plus, here's another one. And actually, this is what I wanted to show before. You could also write HCl, and HCl is naturally a gas, in the presence of water. This is like a solvation equation. In the presence of water forms H plus aqueous and Cl minus aqueous. Okay, and this textbook uses this H3O plus designation. I think that it's better to actually show it here as I've written it, because this is what we're really looking at, because we want those H plus ions to be available. Okay, so what I've done here is I've shown a picture of what this would be, where here you have hydrochloric acid gas above your water. And when you force the hydrochloric acid into the solution, it falls apart and you end up with chloride ions surrounded by these hydronium ions. And that's what's actually happening in our solution. Here's a list of our strong acids, and there's many, many more weak acids than strong acids. There's only about half a dozen strong acids, and these are what we have: HBr, hydrobromic acid, hydrochloric acid, hydroiodic acid, nitric acid, chloric acid, and sulfuric acid. Okay, so here are some of them. And let's just take a look real quick. What are the ions that make these? See, we have HBr, and this is just a review from chapter 2. Is H plus and Br minus, and HCl is H plus and Cl minus, and HI, hydroiodic acid, is H plus and I minus. Then we have HNO3, nitric acid, H plus and NO3 with a 1 minus charge. And then we have perchloric acid, H plus and ClO4 with a 1 minus charge. And these are all what we call monoprotic acids. And that just mono for one protic. Monoprotic means one proton. Okay, and now here we have this other option here. And here we have 2 H plus ions on a single sulfate ion, SO4 2 minus. And this one is what we call a diprotic acid. And that literally means diprotic 2 protons, so 2 H pluses. You also have phosphoric acid, which is triprotic. So most acids are monoprotic. You have a couple of diprotics and a couple of triprotics, but not as many. Okay, a far greater number of compounds behave as weak acids and only partially, usually less than 5%, react with water. Okay, so for an example, only about 1% of acetic acid will ionize, while 99% of acetic acid remains as HC2H3O2 liquid. Okay, so when we put it into water, this is about 1%, and this is about 99%. And so even though only some of it comes apart and becomes water, this is about 1%. Another way to show this, and they show a double arrow to show it going back and forth. Another way to show this that I think sometimes is a little bit better is to say, okay, well, if you have HC2H3O2, so you have your acetic acid and it's a liquid, and you put it in the process of water, then what you'll still do is you'll still have this HC2, HC2H3O2 liquid, and this is about 99%. Well, 99. I'm very messy today. So this is about 99%. If you ever see that squiggly line there, it means about or approximate. And then you have 1% of it falling apart and forming H plus and acetate, C2H3O2 minus, in solution like this. And this together is about 1% of your acetic acid. And again, that's a better way to write it, I think. I'm keeping both methods in there so that when you see it in the textbook, you're like, okay, well, yeah, that's one way to look at it. Here's this other kind of better way to look at solvation. Okay, a base is a substance that will dissolve in water to yield hydroxide ions. And that is definitely one way to describe a base. Okay, a more complex way to describe a base is to say that a base is a proton acceptor. So remember, an acid is a proton donor. It's donating a proton. A base is a proton acceptor, and that's a more widespread use of the term. When we're dealing with strong acids, we're always dealing with that hydroxide coming off. But it gets a little bit more complicated, and especially when you get into semester 2, you're going to have to be looking at it as a proton acceptor instead of creating hydroxides, because not all bases come apart to make hydroxide. But some example of some common bases that we will deal with in Chem 1 are sodium hydroxide, potassium hydroxide, calcium hydroxide, and barium hydroxide. Okay, these bases, along with other hydroxides, completely dissociate water. And again, this is not super true. They don't. Most hydroxides, remember, are insoluble. Okay, so most hydroxides, I'm actually I want to make sure that I fix that. So your thing will look differently than your PowerPoint slides will look a little differently than what I have here. Okay, so these bases, these strong bases will dissociate completely, but most hydroxides are at least mostly insoluble. So are insoluble or slightly slash marginally soluble. Okay, most of them will precipitate out. Sodium hydroxide, potassium hydroxide are the only ones that are really completely soluble. Okay. Some compounds produce hydroxide ions when dissolved by chemically reacting with water molecules. Okay, so in some cases, let's see how you have ammonia here. Okay, and it only produces hydroxide in very small amounts. Ammonia is a weak base, okay, which means that usually we would say less than 5% of it does this. Okay, most of it remains as NH3 liquid or NH3 aqueous in water and does not dissociate. But for the 5% this happens, we would call this an acid-base reaction because one of the hydrogens is moving over to form our ammonium ion. Okay, a neutralization reaction specifically is a specific type of acid-base reaction where the reactants are an acid and a base, and the products are often what we call a salt. And here we don't mean table salt, we don't mean sodium chloride, we mean any ionic compound and water. Okay, and neither reactant is water itself. You can't neutralize water because it's already neutral. And so one example that we have of that is 2HCl plus MgOH2 yielding MgCl2 and water. Okay, and in this case, magnesium chloride is the salt. Well, this is what we would call a molecular equation for our acid-base neutralization. Okay, so this is our molecular equation. We can also write a complete ionic equation for this reaction. Okay, and so we have 2H plus aqueous plus 2Cl minus aqueous plus 1 Mg2 plus. Oh, this is solid. Hang on. No. Plus MgOH2 solid yields. Okay. Now it's aqueous here, so we have magnesium ions plus 2 chloride ions, okay, plus 2 liquid water units. And another kind of hallmark of this is that we can look at our, so our net ionic equation is looking at what's forming specifically. And if we look only at what's forming specifically, then we have 2 protons plus 2 hydroxides yielding 2 moles of water. And that's what's always happening in an acid-base neutralization reaction. All right, so it's time to take a quick break. I'm going to take a quick break, and then we're going to finish chapter 4.